All right, so today we're going to talk about techniques for evaluating limits. So we know we've come up with an idea of what we're talking about when we're talking about limits. We want to know what our function is getting close to as our x gets close to some number. We've looked at graphs, we've looked at tables of values, we have an idea of what we're talking about. What we want to do today is figure out how we evaluate limits without plugging into our calculator, without looking at a graph. How do we simplify? How can we work with our function using algebra to decide what our limit is, so we don't always have to plug into our calculator and do something that way. So, a couple of things. One is all the limits that we're talking about today. X is approaching a number. So for today, we're talking about x is approaching a number. Where we'll talk tomorrow about what we do when x is approaching infinity, positive or negative infinity. We'll work on that separately. So for today, x is approaching a specific number. So the first technique, our book calls it the dividing out technique. So just so you know, when you see that term, I just think of it as simplifying. So the dividing out technique, I think of it as simplifying. So we don't necessarily have to give it a name. The book calls it dividing out. What we're going to do for this particular technique, if we have a limit, we have the limit as x approaches something, and when we plug that number in, the x value that we're approaching, when we plug it in, we use it when we get when we get 0 over 0. So we say x is approaching 2. We plug 2 into our function that we're finding our limit, and we get a 0 over 0. 0 over 0 is called an indeterminate form. And we call it an indeterminate form because 0 over 0 is not necessarily 0. 0 over 0 is not necessarily infinity. 0 over 0 we could end up with some number. So we don't 0 over 0 says you have to do more work. We don't know what it is. And our technique, what we're going to do is basically we want to factor. We want to simplify. And by simplify, we're going to cancel out common terms, that kind of thing. Simplify might also mean, and we did some of this when we were doing trig identities, we might have to add fractions, find common denominators, that kind of thing. So simplifying can mean lots of things depending on what our function looks like. So factor, simplify, and then we find the limit of the simplified function. So we end up with a 0 over 0. We want to simplify so that we get a nice function, a polynomial, a rational function where our denominator isn't 0. And then we can find the limit. So when we simplify, we're coming up with a function that's equivalent to our original after we simplify. So this is what we're going to do. And it's like doing trig identities. There's not one specific way you do every single problem. It depends on what the problem looks like. But normally factoring is going to be a big one. Adding fractions by finding common denominator is going to be another big one, then we simplify. So what I want to do is just look at a couple of examples of finding limits this way. So we good so far? All right, so let's look at the limit as x approaches 3 of x squared minus 9 over x minus 3. So the first thing that I do here is I plug in x equals 3. Can I just plug it in? If I plug in x equals 3, I get 0 over 0. 9 squared minus 9 over 3 minus 3. That's an indeterminate form. That says, got to do more work. So let's write this in an equivalent form. So how can we factor the numerator? x plus 3 times x minus 3. And we're dividing that by x minus 3. Look how nice that turns out. So we can cancel this term. And this is equivalent to the limit as x approaches 3 of x plus 3. And this we can find the limit of. This is just a polynomial. Find the limit of a polynomial by plugging our number in, and that's going to be 6. So the limit as x approaches 3 of x squared minus 9 over x minus 3 is 6. And what does this tell us when we have this common term in the numerator and denominator of this rational function? What happens at x equals 3? There's a hole. So the function doesn't exist, we have a hole at x equals 3. So whatever this graph looks like, our function wouldn't exist at x equals 3. But our limit is 6. The function is getting closer and closer and closer to 6. So our function doesn't exist there, but we do have a limit. Function value is independent of the limit. All right. Let's look at another one. Question Z. How about the limit as x approaches 1 of x minus 1 over x cubed minus 1? If I plug in 1, first thing we do is try plugging in 1. If I plug in 1, I get 0 over 0. I get an indeterminate form. That says, got to do more work. So, we need to factor this denominator. How do we factor this? X minus 1 times x minus 1 times x minus 1. Almost. Not quite, though. It's a little more. Yes? No, that won't work. What if we can't figure it out? So we're on the right track, but if we can't remember how this factors. Yes? So this does factor is to x minus 1 times x squared plus x plus 1. What if we didn't remember that? What if we didn't remember that this perfect difference of perfect cubes factors like this? What technique can we use? Well, right away, if we plug in, we know that if we plug in 1, this function evaluates to 0, right? So that's a 0 of the function. What can we do once we know a 0 of the function? Someone said it. We can divide. And we'll do it the easy way. We'll do synthetic division. So if we don't remember how this factors, we know that x equals 1 is a factor, or x equals 1 gives us a 0. So that tells us that x minus 1 is a factor. So there's our factor. And then we're going to do synthetic division. And when we do synthetic division, we're going to put the 1 on the outside. And inside we have a 1 for the x cubed, a 0 for the x squared, a 0 for the x term, and a minus 1 for this term. Bring that down, multiply, add, multiply, add, multiply, add. Our remainder is 0. We knew this was a factor. So that tells us we have x squared plus x plus 1 after we divide by x minus 1. And that's where this piece comes from. So if you can't remember those perfect cubes, I rarely remember them. I usually have to do this synthetic division. Because I know that 1 is a 0. 1 gives me a 0 of the function. So x minus 1 is a factor. And then I do the synthetic division. Same, opposite, always positive. So if you remember, some people remember, I have a horrible time remembering those acronyms. The thing with for counting the days of the month, how to remember which months have 31 days. See, someone was doing a knuckle thing, but I could never remember is this one the 30 or the 31? And so then finally someone said, well, it's 31, and I said, okay, the first knuckle is 31. So now I'm getting better at it. But for years I couldn't ever remember. I have a horrible time remembering those things. What's that? Right. Okay, yeah. So, but I could never remember that. See, nobody ever told me that before. Yes, right.
There's exceptions, obviously.
All right. And my wife would always try to get me to remember the little poem that 30 days has whatever. And I could never remember what month goes with what. So anyway, I have to do the synthetic division to remember this. So here we factored this. Let's get back to our problem. Oh, and I forgot to write the limit here. So this is the limit as x approaches 1. And thankfully, this helps us out. We can cancel this, and we end up our simplified version after we figured out how many days all the months have. X approaches 1 of 1 over x squared plus x plus 1. And now we just have a polynomial in the denominator. When I plug in 1, I don't get 0, so I'm happy. And this gives me 1/3. So the limit as x approaches 1 of x minus 1 over x cubed minus 1 is 1/3. And the fact that we have this term that cancels in the numerator and denominator tells us we have a whole at x equals 1. So our function is undefined at x equals 1, but the limit is 1/3. So there's a couple of examples. The book calls it the dividing out technique. I just call it simplifying. We're just simplifying and then evaluating the simplified function, evaluating the limit of the simplified function. All right, questions there? Okay, the next technique is called rationalization. And this comes from, it's very much like rationalizing a denominator, very much like we did when we were working with complex numbers and we were dividing by a complex number. We multiplied the numerator and denominator by the conjugate. Same idea. So we use this when we plug in our number that we're trying to, the x value, and we get 0 over 0. So we get an indeterminate form, and we have fractions involving radicals. So this, usually we're going to use the rationalization technique when we have fractions involving radicals. There are other situations when you can use it. This is the most common. We get 0 over 0 and we have fractions involving radicals. So let's look at an example of how we're going to rationalize. So let's look at the limit as x approaches 0 of the square root of x plus 2 minus the square root of 2 over x. So if I plug in x equals 0 here, I get 0 over 0. Square root of 2 minus square root of 2 over 0. So we need to rationalize this. So to rationalize, we're going to multiply the numerator and denominator by the conjugate of, in this case, of the numerator. Okay, thank you. So let's multiply by our conjugate. So I'm going to multiply this, and I'm going to put parentheses there so I remember to multiply correctly. X plus 2 plus the square root of 2. And we're going to multiply the denominator by square root of x plus 2 plus the square root of 2. So that's our conjugate. And we put the parentheses here as well. So then we're going to do our multiplication, and I'm going to say this is the limit as x approaches 0 of, when I do my multiplication here, I get x plus 2, the plus square root of 2x plus 2 and the minus square root of 2x plus 2, those cancel, and I get minus, when I multiply these two, minus 2. And on the bottom, I have an x times square root of x plus 2 plus the square root of 2. Well, this simplifies to the limit as x approaches 0. X plus 2 minus 2, I get x over x times square root of x plus 2 plus the square root of 2. And those two cancel. And finally, my simplified form is the limit as x approaches 0 of 1 over square root of x plus 2 plus square root of 2. And now I can plug that in, and I don't get a 0 in the denominator. We're happy. That's 1 over, we get a square root of 2 plus a square root of 2. So we get 2 square root 2. So this function would have, the graph of this function would have a hole at x equals 0, but our limit as x approaches 0 is 1 over 2 square root 2. So questions there? Yes. So we want to change the sign here in the middle so that when we multiply these out, that the middle term that we get, the square root of x plus 2 times square root of 2 and the square root of x plus 2 minus square root of 2, so that part goes away.
Okay.
So we're,
We only had one from there, we only had square root of x plus 2.
we
You had
multiplied.
square root of x. Then you just have.
Yeah, then you just multiply
Yeah.
multiply numerator and denominator. Yeah. Yes. This would be when I plug in 0 for x, I get 1 over 0 plus, I get the square root of 0 plus 2, square root of 2 plus square root of 2. When I plug in 0 there, and square root of 2 plus square root of 2 is 2 square root of 2. All right, let's look at another one. What if we had this one? And this is similar to one we did in our homework. 1 minus cosine x over x, and our limit is, let me write our limit there. The limit as x approaches 0. If I plug in 0 for x, cosine of 0 is 1, so I get 1 minus 1, 0 over 0. What are we going to do with this? Rationalize? So let's try rationalize. Because we did some of these like this when we were simplifying, when we were doing trig identities. So let's try rationalize. Let's see what happens. So I'm going to multiply by 1 plus cosine x over 1 plus cosine x. It's worth a try, right? So when I multiply this out, I get the limit as x approaches 0 of 1 minus cosine squared x over x times 1 plus cosine x. And that's the limit as x approaches 0 of 1 minus cosine squared x is sine squared x over x times 1 plus cosine x. What's a sine of 0? 0. And I have a 0 over 0 again. Oh, man. Oh.
Why would you tell me that?
It was worth a try. It was worth a try, right? Sometimes you have to try something. You have to try it and see if it works. So what are we going to do now? Rationalize. We could try rationalize again. I think we'd end up back here. What technique did we use in the last section that we know we can always do? What's that? Not much to divide. Not in the last portion. In the last section. What can we do? Let's graph this thing. If we can't figure it out, our fallback for limits is let's graph it. Let's graph it and take a look at it. All right. So let's go to our calculators. I'm going to go to make sure I'm in radian mode. I'm in radian mode. So go to the y equals, and I'm going to graph the function 1 minus cosine x. And we're going to divide that, divided by x. Graph that. There's my graph. So what does this look like our limit's going to be? As x is getting close to 0, my function is getting close to 0. So if we can't figure anything else out, graphing it, looking at a table, looking at a graph, can be kind of your brute force method of figuring out your limit. So this one we couldn't rationalize. It was worth a try. Sometimes that does work with trig functions. We graph it and we see that our limit, this limit, equals 0. So we graph this one. But the rationalizing technique, sometimes it will work, depending on the function. Sometimes you can do that with trig functions, and it makes it turn out more nicely. All right, questions there? It was nice that we remembered this technique, and we also remember that 1 minus cosine squared x is sine squared x. That made me feel good. All right. We've talked a little bit about this next idea before. We're going to come up with a terminology for it and some symbols. One-sided limits. So one-sided limits, we're going to say our terminology, our symbols, limit as x approaches c. And I'm going to put a little positive sign there of f of x. What this is the limit as x approaches c from the right. So we're coming from over on this side, and x is approaching c from this direction. And we're going to talk about a limit coming from the other direction. X approaches c, and I'm going to put a minus sign there of f of x. And that's the limit as x approaches c from the left. Be very careful with this one. It's very easy to confuse this x approaches c from the left with x approaches negative c. Notice our plus and our minus is not in front of the c, it's as a superscript here. So the limit as x approaches c from the left, we're coming from this side, and x is getting closer and closer to c from the left-hand side. And what did we say had to be true last time about the limit from the left and the limit from the right for a limit to exist? They had to approach the same number. They have to be the same. For the limit to exist, the limit from the left has to equal the limit from the right. So if our limit from the left and limit from the right are different, then the limit does not exist. So I just wanted to introduce this terminology, this symbol, so that when we have these limits, these one-sided limits, we know what we're talking about. Nothing complicated here. We're just approaching it from one side or the other side. So let's look at a couple of examples of one-sided limits. One we've looked at before, and another similar to a problem we did before. So let's say we had the limit as x approaches 2 of x minus 2, absolute value of x minus 2 over x minus 2. If we graph this, or we made a table of values, we would see that the graph, and this graph is really important. It's one that you'll become hopefully very familiar with in calculus. The graph looks like this. This is x equals 2, and here we're at 2, and here we're at negative 2. So when x is greater than 2, f equals 2. When x is less than 2, f equals negative 2. So the limit from the right, as we're coming along this way, our limit is positive 2. Our function is positive 2, positive 2, positive 2. From the left, our limit is negative 2, negative 2, negative 2. Our function stays at negative 2. So the limit from the right does not equal the limit from the left. So our limit does not exist. And we can write d in does not exist. So for this function, because the limit from the left is not the same as the limit from the right, left, right, the limit doesn't exist. Now let's look at the limit as x approaches 2 of this function. So our function is f of x equals x plus 2 when x is greater than or equal to 2, and f of x equals x squared when x is less than 2. So if we graph this function, for x less than 2 we have this parabola. And there's x equals 2. And for x greater than or equal to 2, we have a line. Well, at x squared of 2 is 4, and x plus 2, 2 plus 2 is 4, so they connect right there, and I get this line. So the graph of this function looks like this parabola connected to the line. The limit from the right, as x gets closer and closer and closer to 2, my function gets closer and closer and closer to 4. And from the left, as x gets closer and closer to 2 along this parabola, f gets closer and closer and closer to 4. So the limit equals 4. Because the limit from the left and the limit from the right are the same. They're both 4. That's just kind of illustrating that. Yeah, so here I plug in 2, and I see that f equals 4 there, and plug in 2 and f equals 4 there. And if it was some other kind of function where we had to, or there were a rational function or something, then we'd have to do the simplifying with each piece to check the limit on each side. That's a good question. Yeah.
So even though x equals 2 is still like out of the domain or range for the second equation?
Right. Right. So the Joanne's question for the second equation, 2 is not in the domain, but what we're interested in for a limit is what is our function getting close to as x gets close to 2. We don't care what it is when x equals 2, but when it gets close to 2. When x is very, very close to 2 here, x squared is very, very, very close to 4. So that's all we care about. Yes?
So if it's a one-sided function and it says just like x approaches 2 from the right, do we have to check the left too?
So if it were just
Like
this,
for the first
if it were
one?
just this piece,
Yeah,
and it said find the limit as x approaches 2,
or from the right, or would it ever say that?
well, if it said from the right, yeah, that's all you'd have to worry about is this part.
So we
And
don't have to check the other?
no, because the function isn't even defined there. So all you need to worry about is as we get close to 2, what's my function close to? All right, questions on one-sided limits. We've worked with the idea already. The bottom line is we need the function, the limit from the left to be the same as the limit from the right. And when we talk about limits a lot, we do this thing. Limit from the left, that's limit from the left and the limit from the right are not the same, the limit doesn't exist. When you're in calculus, you'll be doing this kind of thing a lot when you talk about limits. All right, last thing I want to do is actually a limit from calculus. Just to look at to a preview of a technique that we'll use in section 11.3 on Monday. All right. So we want to find, we're going to say f of x equals x squared minus x. We want to evaluate the limit as h approaches 0 of f of 1 plus h minus f of 1 over h. And what we're looking at, this is called the difference quotient. What we're looking at here is the slope of the function at x equals 1. This is the equation of our slope at x equals 1. We're letting this is our rise, and h is our run. And we want our run to get very, 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 very small, so we just get the slope at that one point. And this is going to be a very important, one of the main ideas, one of the two big ideas of calculus that you'll talk about next year, is the slope at a point. So let's evaluate this limit. So this is telling me to plug in 1 plus h for x. So this is going to be 1 plus h squared minus 1 plus h. And then we're subtracting f of 1. So that's going to be 1 squared minus 1 over h. So this is just another way of simplifying a limit. Here I'm plugging my things into my function to simplify my limit. Plugging 1 plus h in for x, 1 plus h squared minus 1 plus h, and then plugging 1 in for x right here. So let's simplify this. So this is the limit as h approaches 0. I'll square this, expand this out. So this is 1 plus 2h plus h squared minus 1 minus h. Just distributing there. And 1 squared is 1, minus 1 is 0. So that this whole piece goes away. And I'm dividing by h. Oh, and I don't want limit equals, I want it equals a limit. Equals a limit as h approaches 0. The minus 1 go away. 2h minus h, I'm just left with an h. So I get h squared plus h over h. 2h minus h gives me the h. Get the h squared there. Limit as h approaches 0. I'm going to factor out an h here. And now we see this is how this is related to our dividing out technique. Those cancel. And I get the limit as h approaches 0 of h plus 1. And that gives me 1. So the slope of this curve, x squared minus x, at x equals 1, would be 1. And we could use this process to find the slope of that curve at any point. And we'll do more with this later. All right, questions on what I did there? Okay. Homework. All right, there we go.